Well, you do remember that some time ago we brought up Ernst Mach, right? And what was associated with his work, which was Mach's principle, right? So Mach had this idea that he criticized the way Newtonian mechanics was set up, and in particular, Newton's idea about inertia, because Newton thought that anytime you have some sort of acceleration, that acceleration would be referred to absolute space. And Mach thought that this idea of having absolute space was just metaphysics. So what Mach suggested was that instead the idea of absolute space should be based on something that is physical and observable. So he said anytime a body resists acceleration due to inertia, it is due to the fact that it is interacting with the rest of the universe. So at that time, Mach conceived the idea that inertia was due to the distribution in far away, what we would refer today as galaxies, right? So based on that, we would come to the conclusion that any sort of inertial forces, right, that arise when you have an acceleration or if you have a rotation, those inertial forces, according to Mach's principles, are due to the distribution of faraway galaxies. So then the question comes up, to what extent does general relativity include these concepts? So in other words, is Mach's principle part of general relativity? Is it not included at all, or is it included to some extent, right? So Einstein, of course, was very interested in that very early on. He was well aware of Mach's work. And so he started actually doing calculations that were relevant to this very early on. 1913, he did some work with Besso. And soon after that, after the theory of general relativity was written down in 1916, a guy by the name of Lense-Thirring and one of his collaborators by the name of Joseph Lense decided to actually do a calculation in the relativistic theory, right? Because of course the original calculation of Einstein and Besso was done in the old theory, this C-field theory, which was not the correct one. Right? So they decided to do an actual calculation in GR to see whether you would have something that would be a reflection in some way of Mach's principle. So what they decided to do is to have the following setup, right? So it's kind of an idealized setup where you have a thin spherical shell, which is has some mass m, right? And that thin spherical shell is rotating about an axis like this with an angular frequency which is omega 0. And now you ask what happens at the origin. If you suspend, for example, a pendulum at the origin, when this spherical shell is rotating, will it drag the movement of the pendulum? So in other words, will the pendulum feel the effect of the fact that this mass is rotating, right? So the idea of Lense and Thirring, right, this is 1918 paper. The idea of Lense and Thirring is just to replace the whole of the universe by just this thin spherical shell, so there's nothing else anywhere, right? So you try to solve the equations of general relativity, right, the field equations, given that you have this spherical shell, which is assumed to be very thin, right? Very thin. And so if you look in the, if you want in the equatorial plane, then looking from the top, then you have this shell, right, that is rotating, right? It is rotating like this with this frequency omega naught, right? And now you have, at the origin, you have some sort of Foucault pendulum, right? Remember the Foucault pendulum is that pendulum that you can find, for example, in Paris, suspended from the ceiling of a tall building, which indicates the effect of the rotation of the Earth, right? So the pendulum always swings in the same direction, but the Earth is rotating, and therefore the plane in which the pendulum is swinging, slowly rotating, right? So you have that, then the direction in which the pendulum is rotating is well, that direction is going to shift by some angle. And in fact, there's going to be some frequency, right, that is associated with that, some angular velocity that will describe how the plane of the pendulum is moving, right? And so this is the calculation that Lense and Thirring set about to do. And so we have that this mass shell is at a distance r from the origin. So we'll be interested what happens at the origin here. And well, this distance will be fairly large. And of course, we have a body which is, in this case, completely spherically symmetric. And so it means that in our case, we are going to have a T naught naught, which is different from 0 just in this region, right, inside the shell. And it turns out that the Tij also is different from 0. So you have both of these that are non-vanishing. And so then it's a question of working out the consequences of field equations to find out what you get, right? Well, Lense-Thirring, of course, were originally, due to the difficulties in dealing with this problem, were not able to solve the field equations exactly. So they resorted to the weak field expansion. Weak field expansion, which meant that they also called, in this case, the post-Newtonian approximation, right? Post-Newtonian approximation, because you can actually do a systematic expansion of the metric in terms of a certain number of fields which are well suited to describe post-Newtonian physics. And those fields, as we'll see in a moment, are a little bit like the vector potential and electromagnetism. So anyhow, there is also a long discussion about this in the book, and we won't go through it and just state the basic facts that in this weak field or post-Newtonian approximation, in the post-Newtonian approximation, by the way, one does not just assume that the fields are weak, but one also assumes that the velocities are small, right? And in fact, in this case, we are going to be interested in this sphere rotating at an angular velocity which is fairly low, right? So in this set of approximations, we have that G naught naught is going to be set equal to -1 minus 2 phi plus dot dot dot, and the Gij is equal to delta ij, right, minus 2 delta ij times phi plus dot dot dot, and where phi is the Newtonian potential. And well, it will be crucial and necessary in this case to have the Gi naught to be non-zero, right? So Gi naught is going to be equal to something that has just a spatial index I, which is some sort of vector potential for the gravitational field, which we're going to denote by psi. Psi I plus higher order terms, right? And so, of course, all these fields depend on x and t, so we have psi of x and t, and we have this psi I, which also depends on x and t, right? And so you insert this in the field equations, and we're not going to go through the details, but you will find that after a little bit of work, the psi vector is then determined. This vector potential is determined by the field equations to have this form. Psi is equal to 2g divided by r cubed times x cross j, where j is the angular momentum that is associated with the rotation of this body, plus terms which are of order 1 over r cubed. Right? This is what Lense-Thirring calculated initially. And so this can be rephrased as psi vector is equal, can be rewritten entirely in terms of this angular frequency as x cross omega. X cross omega, where omega, well, it is not quite the same as omega naught. Well, it does point in the same direction, right? So the two angular velocities have the same components. In the direction is the same, but the magnitude is different. So omega is equal to minus 4/3 times the phi potential times omega naught, right? And so this was the original result of Lense-Thirring that was derived in the limit in which the angular velocity is small and the fields are weak. And this formula, of course, is very similar to what you have in electromagnetism, right? When you look at the vector potential for a magnetic dipole, right? If you have exactly this, the J here plays the role of the magnetic dipole, and the psi plays the role of the vector potential. So the calculation is quite similar to what you would do in electromagnetism. And so now you need to estimate what the potential is, right? And so the potential in this case is just an integral of the T naught naught over the region where the T naught naught is non-vanishing, right? So phi is equal to minus 4 pi times g, right, times the integral in d3x prime, right, over this shell, right, of the T naught naught. And the T naught naught will depend, in fact, only on the r prime. So sorry, we already taken out the angular factor. So this is just r prime times dr prime. And the integral is just over the region where the mass distribution is non-zero, which is this outer shell, which is supposed to be thin, right? So it will have an intrinsic diameter, but I mean an intrinsic shape, but that width is supposed to be rather small. And so this integral is 1 over 4 pi times the mass divided by the distance, right? And so we obtain that omega, so we put that in here, right? So this Newtonian potential is given by that expression, so the 4 pi's go away, and we have that omega is equal to omega naught times 4/3 times gm over r. And if you put in the speed of light, then it's this result. Right. So that seems to suggest that, in fact, there is some truth to what Mach originally thought. So this is Relativity, 1918, right? That in fact you have that there is this effect of frame dragging, right? That the pendulum is in fact going to change the direction in which it swings, like the plane in which it swings is going to rotate with an angular velocity which is, well, is not quite the same as the velocity at which the whole shell is rotating, and the relationship between the two is given by this extra factor of 4/3. But nevertheless, of course, if this combination happens to be of order 1, then you do have that omega is the same as omega naught, right? So omega is the same as omega naught if you have that gm, right? If gm divided by rc squared is of order 1, right? And so in that case, in fact, all that matters is the fact that this mass distribution is rotating. The pendulum will rotate with it, and that provides this reference frame that Mach was talking about. Now, of course, the shortcoming of this calculation, right, is that it is done in some sort of weak field limit, right? So you're assuming that the fields are weak. And of course, what appears here is precisely the combination of quantities that you do have in the case of the Schwarzschild solution, right? So you might worry that this has to be carried out to include the case of strong fields, and so that was not done for a while because the problem seemed somewhat complicated until Brill and Cohen decided in 1967, I believe, yes, Brill and Cohen in 1967 decided that they had a way of doing the solution in the strong field limit, and what they did is they used the Kerr solution. Now remember, the Kerr solution, which we actually haven't talked too much about it, but we are going to have a presentation very soon about it, is the analog of the Schwarzschild solution when the mass is rotating. Right, so there you consider a rotating mass, so there's angular momentum that is involved, and the metric has a somewhat more complicated form than the Schwarzschild metric because of the rotation, right? And so what Kerr had obtained was an exact solution to the rotating black hole. And what Brill and Cohen did is they considered that type of solution when you had an infinitesimally thin shell that was rotating, right? Well, normally, of course, the Kerr solution applies to the exterior region, but Brill and Cohen were actually able to analytically continue the exterior solution for a thin rotating shell to the interior, right? And when you analytically continue to the interior, then you have precisely this kind of setup, right? And so the conclusion they came to was that omega, this result is essentially correct, but the factor in front is changed, right? So in their calculation, they found that omega is again equal to omega naught times 1 divided by 1 plus 3r divided by 1 plus beta times 4 times mg, and then times 1 minus 2 mg over r, capital R. Right? And well, now if you look at this expression, what happens is that in fact when R is about equal to 2 mg, then omega is the same as omega naught, which is again precisely what Ernst Mach was talking about, right? That when you have the right conditions, right, which is that this radius is somehow related to Newton's constant and to the mass in the thin shell, then in fact the pendulum at the origin will rotate with exactly the same frequency, and everything will look static, right? Everything will look static, right? So that comes back to the issue of what happens, right, when you're in the middle of nowhere between planets, right, and you rotate yourself, for example, about an axis, right? Your arms will go up, and but normally when you don't rotate, your arms do not go up. So what is the difference between the two? Well, the difference is, of course, in one case you're rotating with respect to the faraway galaxies, and in the other case you are not, right? So the state of absolute absence of motion is the one where you have you're just rotating with the same angular velocity with respect to these large mass distribution at infinity, right? So if Mach principle is exactly satisfied, right? If Mach's principle is exactly satisfied, then you have to have that omega is about the same as omega naught, which means that for Mach's principle to be exactly satisfied, you have to have a relationship of this type, right? And so now you can check. So for our universe, right, you can check for our universe whether something like that is anything close to the truth, right? Because you would expect that, so if Mach is correct, then there should be a relationship of this type, right? So the first thing you can calculate is 2 times mg, right? And, well, 2 times mg would be, well, first of all, the mass of the universe. The mass of the universe. Well, that, of course, is not very well known and understood, and we're talking about the mass of the visible universe, right? What we can actually see. And but that we can say that presently cosmology tells us that the mass of the universe is of the order, right, of something like 10 to the 80 protons. So 10 to the 80 times the mass of the proton, give or take a few orders of magnitude. And then we have, of course, the Newton's constant. So Newton constant is well, we can put in actually the coefficient in front. It's 1.6162 times 10 to the minus 33 centimeters squared. Remember the Newton's constant, if you use units where h bar and c is equal to 1, has dimension of a length squared, right? And now the mass of the proton, you want to express that in centimeters. So the inverse of the mass of the proton is the Compton wavelength of the proton. That's about a Fermi, right? So we're talking about 10 to the minus 13 centimeters. So this is 4.7 times 10 to the 13 centimeters to the minus 1, right? So you put that in there, right? And so that gives about 1.23 times 10 to the 28 centimeters, right? So 2 mg from the known features of the universe at this state, visible universe, is of the order of that length scale. And now we can repeat that for R and see if we get a similar scale. So R is the size of the visible universe, right? And we can take that to be roughly of the order of the Hubble constant, right? So that's about 13.8 gigayears for the age of the universe. 13.8 gigayears expressed now in centimeters. That is about 1.31 times 10 to the 27 centimeters, right? So those numbers are close, and so if Mach is correct, if Jordan, Brans-Dicke, and Sham are correct, if Feynman is correct with all his arguments that we discussed some time ago about the magnitude of the metric having something to do with the distribution of mass in the universe, then G is related to cosmic quantities, right? This argument says that G, right, that G is about R divided by 2m, right, something of that order. Right, so if that is correct, of course, it means that G has nothing to do with particle physics. Right? Newton's constant has to do with the distribution of mass in the universe. If these arguments are correct, if Feynman is correct, if the Mach principle has anything to do with the real world, then the value of Newton's constant is unrelated in any way to particle physics, and instead it has something to do with the total mass and total size of the universe in a way that within this simplistic calculation is reflected in a relationship of this type, right? So anyhow, this is what Lense-Thirring did, and so I think it's a very interesting calculation, and it sheds, again, new light on this very important aspect, fundamental aspect of general relativity, namely whether general relativity actually does include to the full extent Mach's principle or not, and which is something that has come up over and over the years and was in fact the motivation, the main motivation for the Brans-Dicke theory, right? That was a very interesting theory in which you try to then go, if you want, one step beyond this, right? Because in the Brans-Dicke theory you say that G is related to this cosmic field. 1 over G is this Brans-Dicke field. And so that was the first attempt to actually include these kind of discussions into a dynamical theory. And as we know, that didn't do too well, right? Because the Brans-Dicke theory contains this parameter lambda or omega. And already at the level of solar system tests of GR, the Brans-Dicke theory is not doing too well. Some of the parameters have to be really small, and otherwise it just doesn't work. So. Anyhow, we are going to leave now this subject of, well, the Lense-Thirring effect and, in general, what happens to the kind of solutions that one gets, which are similar to the Schwarzschild one, and instead look at a completely different context, which is the context of cosmology, right? So we are going to look at Einstein's equations in cosmology, right? And so at much larger scales than what we have looked at before. And so we want to understand what Einstein's equations, which are of course relativistic, right? So they can describe, for example, not only arbitrarily strong gravitational fields, but when those gravitational fields are coupled to matter, they will be able to describe both non-relativistic matter, like just ordinary stars, but also relativistic particles like neutrinos and photons and so forth. So we want to understand what those equations have to say about the evolution of the universe on very large scales. And of course, on very large scales, the only force that is relevant is the force of gravity. Right? It's the only one that really matters on very large scales. So that's the domain in which Einstein's theory is most suitable, of course. And so we want to understand what those equations tell us. And we have to understand from the very beginning that the Einstein field equations are not going to answer every possible questions about the evolution of the universe, because we will have to know, in order to actually write down those equations, what the source terms are going to look like, right? The source terms are going to be determined by the energy momentum distribution of matter. So we have to have some observational input on what that is going to be. And of course, we are going to use a simplified metric, right? Because we are going to assume that the universe is homogeneous and isotropic. Right? So homogeneous means that the way I describe it, it's going to be the same way as some other guy describes it on some faraway star or even faraway galaxy, right? It will look the same pretty much everywhere as far as the equations are concerned, right? Which in a sense is just the Copernican hypothesis applied to the universe as a whole, right? Copernicus has stated that the Earth is not at the center of the universe, and so we can state today, right, that even from a cosmological point of view, we're of course not at the center of anything. We're just at one specific location. So the homogeneity assumption says that things are pretty much the same everywhere. And the isotropy, of course, states that whichever direction you look at, the universe will look pretty much the same, that there is no significant angular dependence. So then the question is, to what extent are those two underlying pillars, underlying assumptions, to what extent are they actually based on observation? And well, if you look at the distribution of matter around us, of course, it's neither homogeneous nor isotropic. But if you look at very large scales, then it starts to look more and more homogeneous and isotropic, right? Of course, we have mass distribution nearby, especially when you look at our galaxies. Of course, it's far from being uniform because we have a specific structure due to the way the mass is distributed in our galaxies. But when you look at distances which are beyond the individual galaxy and start to look at the distribution of clusters of galaxies and so forth, then the assumption of homogeneity and isotropy is not a bad one at all. And so we're going to start from that, clearly based on the fact that if you really want to go beyond some simple metric, then the problem starts to become rather complicated, right? Then you have to solve equations that are no longer based on some simple metric with some simple symmetries. And so that is one ingredient, right? We do know what the equations look like exactly, but we have to make some assumptions about the metric. The other assumptions, of course, we have to do is about, as it always happens in some sort of classical situation, is you have to make assumptions about the initial conditions, right? And well, the initial conditions, no matter how you slice it, we don't know them. We don't know them, right? So you can claim that you know them, but I think at some point it just gets into metaphysics, right? So people will say, well, the initial conditions have to be simple. And I think Feynman's reply to that was, well, if it really has to be simple, then we might as well have a universe which is devoid of anything, because that's the simplest, right? So it's not obvious that things are going to be simple in any way. And we should probably not assume that they are simple. We just don't know, right? So what we do know is that we can see the present distribution of matter and radiation in the universe, and we can, based on Einstein's equation, which we think are correct as far as the evolution of gravity and mass distribution, we can run the movie backwards. We can run the movie backwards, and we can make all sorts of very precise statements about what happened in the early universe. And of course, we can compare that with observation, because we can look back. We can also look back, right, and compare observation with what Einstein's theory predicts. And the agreement, of course, is very good, right? We know that right today in 2014, we know that the description of the universe based on Einstein's equations fares very well. We have to introduce the cosmological constant, right? That's an important ingredient. It has to be there, otherwise things don't work out very well. But once you introduce that, and you assume that you have matter, and you have radiation, and you have photons, and you have neutrinos, and so forth, when you put everything together, it works extremely well, right? But then, of course, when you run the movie further back in time, then at some point, you don't quite know what is going to happen, because the laws of physics become a little bit more foggy, right? We do understand nuclear physics very well. We understand how eventually when you go past nuclear physics, you have quarks and gluons, and you have the particles of the Standard Model, but then eventually things, might at some point become a little bit less understood. And then, of course, the problem comes up, what happens at the singularity, because when you run back the movie back in time, you end up with a situation where the density is extremely high at about 13.7 billion years ago. You have an extreme density, and so then at that point, views by different people start to diverge, right? Some people say, well, you will have string theory, right? You will have that particles are no longer point-like, but they're described by strings, in which case perhaps you have a bounce, right? So the thing just contracts to something close to a point and then bounces back. So there was perhaps a universe before that. I think one of the proponents of this scenario had a beautiful idea, right, by Gabriele Veneziano, that the beginning of time is only a myth, right? That in fact there was no beginning of time. There was perhaps a universe that evolved into a singularity and then bounced back. And this was due to some laws that we might or might not understand completely, based perhaps on the interactions of strings or something else. And so the way we see the initial conditions, of course, in that framework is the way we see them is because they arise from some other condition before that, some other universe that collapsed into a point, or maybe there was something else. Maybe there was a true singularity. And of course, people, when they look at mathematical equations, they don't like to deal with singularities, right? So one would like to find a way by which actually you don't have things that are singular. Generally, Einstein's equations tend to lead to singularities. We already have seen, for example, the way horizons appear in the Schwarzschild solution. And so there's going to be more singularities when you run this movie back in time. But that might just be an artifact of the fact that we don't have yet a complete understanding of what happens in the very early universe. So this is just a short way of trying to understand that we do have a set of equations. We do have a set of observational data. We are going to make some simplifying assumptions about the metric. And that what we'll get out of it is not going to be an explanation of the universe as a whole, but only of some aspects of it, right? That the basic question of what the initial conditions were is basically not known, no matter what anybody will tell you, right? They are not known. We can just run the movie backwards in time based on Einstein's equation and everything else that we know about nuclear physics, and that is what physics tells us, right? And beyond that, some of it can become metaphysics, right? It can become metaphysics because you then assume that you have the simplest scenario, but what is the simplest scenario to me might not be the simplest scenario to James, right? So we might have different ideas of what is actually the simplest and most beautiful and most elegant and most economical, right? So we have to keep those aspects separate, right? And so nevertheless, as I said, Einstein's equation gives some extremely clear and unambiguous predictions about certain things, right, which follow from the field equations, right? So if you take the field equations as the fundamental equation for gravity, as we discussed in this class, then you assume what you do get is a solution for the metric that comes out of those. And so we have to assume that the metric has a certain form, and we are going to assume that the metric describes a universe which is homogeneous and isotropic, right? Now remember, the Schwarzschild solution was static and isotropic, That is no longer going to be the case here. Not static, right? We want to account for the fact that there is an evolution. The equations will tell us that is what is going to happen, right? And so we will have the static is gone. We're going to have time dependence. And well, it's still going to be isotropic because of what I discussed a moment ago. But we will assume that the physics is basically the same everywhere, right? Actually, one of the interesting aspects that will come out of it, as we'll see in a moment when you just write down the metric and look at simple solutions, is that even though the field equations are generally covariant, right? And you remember that general covariance is a kind of extension of special relativity. And special relativity says that space and time are all on the same footing, right? So general relativity is based on this idea that space and time are pretty much the same. Nevertheless, of course, the solutions and the metric that we write down at first, but the solutions of the field equations will not obey the principle of special relativity because time will be special. Time will be special, right? There's going to be a singularity when you go back in time, right? So this symmetry between space and time is kind of going to be broken by the solution. Not the equations, because the equations, of course, they're perfectly symmetric because they obey general covariance, right? But the initial conditions, the whole setup based on this metric is going to treat space and time components differently, right? So the metric we're going to write down is d tau squared is equal to dt squared minus r squared of t, right, times the r squared times 1 minus k r squared plus r squared times d theta squared plus sine squared theta d phi squared. And then close parenthesis like this. Right, so that is going to be our metric, and this is called the Robertson-Walker metric. Robertson. Metric, right? And so this is the metric that embodies this principle of homogeneity and isotropy, right? So what is K? Well, K turns out is equal to just 0 or plus or minus 1. And so the isotropy, of course, is in this part. The isotropy is in this part, which is spherically symmetric, if you want, right? And the homogeneity is in that part over there. Notice that in particular here there is a coefficient of 1. Right? Remember that when we looked at Schwarzschild solution, there was a function b here, right? That function b determined the rates of clocks, right? And was different from one point to another. Here, the function that determines the rates of clocks is always the same for all observers. So this time t is usually referred to as cosmic time, right? So this is the time, in fact, for freely falling observers because the coefficient of proportionality here is 1. So now the question is, how do you justify something like this, right? Because I think it is important that at least within the context of this class, we just don't write down a metric and then proceed to a solution, but provide some sort of understanding of where it is coming from, right? So even though this is not really a derivation, we will nevertheless give some arguments of where that is coming from. Right? So what we consider here is a set of space-like hypersurfaces. Right? So this is this direction is our xi. Right? This direction is our xi, and the direction that is perpendicular to it is the time. So we're looking at different observers that are located at different positions in space. And the direction that is perpendicular to this space-like hypersurfaces is what we associate as, we describe as time, right? So as a result of that, the d tau squared, we're going to write it as dt squared, right, minus some spatial metric, which is gij of x and t, right? And let's write this as xk, right? And then dxi and dxj. Right. So we take into account the fact that, as I said, this time is just the proper time that is associated with an observer, right? And so as a result, it has this coefficient of 1. And now we want to use the fact that we also have this isotropy, right? So we are going to write that gij of xk and t that this, first of all, is not going to depend on where we're at, right? So the homogeneity. The homogeneity is going to come in by the fact that there is an overall scale which only depends on the time. So that scale we write as r squared of t, right? And then times some metric, hij, which does not depend on t anymore. So it's an hij of xk, right? And so it's on that hij of xk that we're now going to use the isotropy as well. Now this part here, we're going to give it a name and call it dl squared. Right? So the dl squared is the distance in real space as opposed to four-dimensional space. And so the dl squared is, of course, determined by this spatial metric. And the spatial metric, because of homogeneity, is going to be some scale factor, r of t, equal some scale factor that determines the overall scale times a reference metric which is independent of t. Right? So, well, we're at the stage where we have this piece here. We have the overall scale factor, and now what we need to justify is the writing of the gij in this form, right? And well, of course, if k is 0, then we have just a metric that is associated with flat space, and so there isn't really much we need to justify there. The problem is, how do you bring in the fact that you can also have k equal to +1, and why is it that in the end it just comes down to only these choices of integers, that k is only plus or minus 1 or 0, right? So the simplest case is, of course, flat space, so we're going to discuss that first, right? So we focus now. Right, so we focus now on this hij, which depends on just on the xk, right? And so the first case is flat space, right? And for flat space, of course, we have that dl squared is equal to dx squared plus dy squared plus dz squared, right? And well, in spherical coordinates, that is what we have over there when k is equal to 0. So in spherical coordinates, this is dr squared plus r squared times d theta squared plus sine squared theta times d phi squared. Right? And so that's the end of it. Now, the next case is a little bit more complicated, and that is the surface of a sphere. The surface of a sphere. So let's come to that, and we shall see that the surface of a sphere, the spatial metric for the surface of a sphere, can be written in this form when k is 1. Right? So let's see how that comes about, because it's not obvious. So B is a surface of a sphere in 4D Euclidean space. Right? So we embed this in 4-dimensional Euclidean space. And so the surface of a sphere is, well, first of all, have coordinates x, y, z, and w. X, y, z, and w, right? But we want to have the surface of a sphere, which means there's a constraint that x squared plus y squared plus z squared plus w squared is equal to 1. Right? It's a unit sphere. We don't need to consider a sphere that has the arbitrary radius, because the size of the sphere has already been taken into account by the scale factor, by the r. Right? That's the radius. The capital R of t is the radius. So we're not looking at the sphere that has a unit radius. And so, of course, this relationship here, we're going to use that in a little bit, implies that, that of course, 2x, if we take the differential, right, 2x dx plus 2y dy plus 2z dz plus 2w dw, and so forth is equal to 0. Right? And so that will allow us to solve for dW in a moment, right? So we'll come to that in a second. And so now we write x. We introduce spherical coordinates. But of course, spherical coordinates in one dimension more than what you're used to, right? Because we have 4 coordinates and not 3 to start with. So we write x as sine chi times sine theta times sine phi, cosine phi, sorry. Y is equal to sine chi times sine theta times the sine of phi, and z is equal to sine chi times the cosine of theta, and w is equal to the cosine of chi. So these are spherical coordinates in one dimension more than we're used to, and because of that we have that the angle, the new angle is between, the new angle chi is between 0 and pi, and the angle theta is as usual also between 0 and pi, and the only one that is between 0 and 2 pi is the angle phi, right? And well, you can verify that of course this solves the constraint, right? When you plug it in, you get that the squares are all equal when they add up to 1. Right, so now we write the distance of the line element on the surface of the sphere, right? And so that is dl squared, right? So dl squared is of course equal to dx squared plus dy squared plus dz squared plus dw squared. Right? No question about that. That is the distance when you go along an arc on the surface of the sphere. But now we use this dw is equal to from here. Right? So from the constraint we can actually solve for dw. And so we can write this as being dx squared plus dy squared plus dz squared, of course, again. And now the dw is going to be, so plus x dx plus y dy plus z dz, right? And then squared divided by, well, we have to divide by w, right? But w is 1 over, you can solve that, right? Or w squared is 1 minus x squared minus y squared minus z squared, right, for w squared. Okay, very good. So now we can rewrite this in spherical coordinates. Right, so we want to rewrite things in spherical coordinates, so we're going to use this relationship at this point, which we haven't used yet, right, to get to that. Okay, so this is equal to d chi squared plus sine squared chi times d theta squared plus sine squared theta times d phi squared. Okay, very good. Well, that still doesn't look like what we had a moment ago from the Robertson-Walker metric, nor does it look like the usual distance in spherical coordinates, but that is very easily accounted for by simply setting r is equal, so let me write this over here. So set r is equal to the sine of chi. And so if we do that, then, well, again, this d chi squared is not just simply dr squared, while this, of course, is just exactly r squared, right? So we get, in fact, one of the forms for the Robertson-Walker metric, namely we get that dl squared is equal to dr squared divided by 1 minus k r squared, right? Which is this part here, right? and then plus r squared and times d theta squared plus sine squared theta times d phi squared. Okay, so now that looks very much like, what does it look like? Well, of course, it looks like the line element in Euclidean space if we didn't have this term, right? So it looks almost exactly the same, and that's, of course, the whole point of this transformation, is to bring it in a form which is almost identical to the flat space one. And the difference, sorry, there is no k here. It's just a 1, right? So, in this case, we do have that k. So same as, let me write it, same as the Robertson-Walker we had at the very beginning with k equal to 1, right? And so, and of course the Euclidean one is when k was equal to 0, right? When this was, the r squared wasn't there, and then that's the Euclidean one, right? So we have that k equal to 0 is a flat space. And k equal to 1 is the surface of the sphere, right? Surface of a sphere, so sphere in 4-dimensional space where we just look at the surface. And so that leaves the case of k equal minus 1. Right, so we can write this together, these two, we can write as dl squared is equal to dr squared times 1 minus k r squared plus r squared times d theta squared plus sine squared d phi squared, right, like this. So we can have those two cases, k is equal to 0 and plus 1, right? So that leaves the third case, which is k equal to minus 1. So k equal minus 1 is also allowed. K equal minus 1 is also allowed. And so what is that object? Well, that object is a so-called pseudosphere. An object is a so-called pseudosphere, so it obviously does not correspond to a sphere, but it corresponds to something that is referred to as hyperbolic space. Right? And it's something that, well, of course, the sphere we visualize as something that looks like this, right? Right? And so hyperbolic space is, in fact, not bounded. We have something that looks more like that. Right? And so this hyperbolic space, well, you can see the appearance of the curves that look like hyperbolas is in fact another possibility as well. So we can have that as well. So this would correspond to the case k equal to 1. This would correspond to the case equal minus 1, right? And so, and then of course we have flat space, right? And flat space is just like that. And so this is k equal to 0, right? And so because of the nature of the geometry of those three metrics, so the form of the metric for those two cases, we describe this k equal to plus 1, so the explicit plus 1, as a closed universe, right? This one as an open universe, right? And k equal to 0 as flat. Right? And well, we can already see here that the choice of metric somehow seems to bring in the nature of the boundary conditions at infinity, right? About which we know very little, right? And so nevertheless, the Robertson-Walker metric does allow for, even when you require that the metric be homogeneous and isotropic, you do have a number of different options that have to do with this parameter k, right? In particular, what is interesting is that this k only needs to be an integer, namely there is no continuum of different manifolds, but there's just three choices. K0 plus or minus 1, right? So that, of course, is a great simplification. And so that is supposed to provide an argument of why, in fact, we can just stick to a metric that has this form, right? So we have given the justification for why the metric now is d tau squared. The line element in four-dimensional space-time is equal to d tau squared equal to dt squared minus r squared of t times this, right? Where we now here have a k, right? So this is our Robertson-Walker metric that expresses, so it does express the constraint of homogeneity, isotropy, and the fact that we do have, in fact, three possibilities for the parameter k that appears here depending on whether we have an open, closed, or flat universe. So k is equal to 0 or plus or minus 1. Right, so that is great, and of course it's a great mathematical simplification. It's an assumption that we, in order to get a solution to the field equations, we assume that this is all there is to the universe, right? And tremendous simplification. Nevertheless, it is a metric for which we can work out quickly the solution analytically, and in fact we can get an exact solution, right? There is no need to approximate anything. We don't need to require some sort of weak field limit, right? The full nonlinear equations, you can find a solution for this without too much work, right? So we'll proceed to do that at this point, right? And so one new ingredient, of course, that we have is when we try to use these equations to describe cosmology, to describe the universe, right? There's one function here. Right, there's only one function, so that's all we need to get an equation for, is for this r of t, and then we're done, right? So at that point, of course, that looks even simpler than the Schwarzschild solution, right? Because the Schwarzschild solution, you had two functions. You had a of r and you had b of r, right? And then it turns out that when you write down the field equations, in that case, are just the fact that the Ricci tensor has to be 0, you find that a is 1 over b, right? And then you get a solution quickly from that. So here it's even simpler, right? Because we just have the scale factor appearing in the metric, not two functions, but just one. Well, nevertheless, the problem is just about as complicated because we also, in this case, have a source term which is not 0. Right? So in the case of the Schwarzschild solution, the source term was 0. We just had r mu equal to 0. Right? The source was essentially considered as a delta function at the origin, so we had vacuum solutions everywhere except perhaps at the origin. And in this case, that's not what we want to do. We want to have a distribution of energy momentum somewhere. So we have that the T mu nu, of course, is different from 0. The T mu nu is different from 0. So we are going to have the field equations, right? R mu nu minus a half G mu nu R, right? Plus, sorry, minus lambda with Weimar convention. Minus lambda G mu nu is equal to minus 8 pi G T mu nu. Right. And so the metric, of course, will go in there, right? It also appears in the T mu nu, but nevertheless, the T mu nu now, which is the right-hand side of the field equation, is also going to be non-zero. And so what is the T mu nu for all the stuff that is in the universe? Right. Well, again, we have to make some simplifying assumptions, and the simplifying assumption is that this is going to be described by a perfect fluid. So that means that it's going to be a fluid that has no viscosity, right? To a first approximation, it is the simplest fluid that we can think of, and that is actually a reasonably good description of both non-relativistic matter, right, and also of photons, right? And so that is going to be, so it's a perfect fluid, so that means that T mu nu is going to be equal to rho plus P times U mu U nu, right? And then plus P, the pressure term, which is G mu nu, right? And so we will be after functions P of T and rho of T that satisfy the field equation as well. So we are going to have, in fact, 3 functions that we need to determine, and not just one, not just a scale factor. Well, it turns out actually the problem is not that complicated, because usually there is an equation of state that relates rho to P, right? There is an equation of state that tells us how the pressure is related to the density, right? And so we'll come to that in a moment. And there's actually just basically 2 cases we'll be looking at where the density is proportional to the pressure. And in one case, the pressure is essentially 0, which is non-relativistic fluid. And in the second case, the pressure is 1/3 times the density. So usually we can get away with writing P is equal to W times rho. P of T is equal to some constant times rho, where W is either 0 or 1/3. And in fact, the cosmological constant case is -1, because when P is equal to minus rho, then this term goes away, and we just have the G mu nu, which is precisely what you have for a cosmological constant term. Anyhow, the other simplification is that this for velocity, what is this for velocity? Well, with the choice of the reference frames and the Friedman-Robertson-Walker metric, we're actually dealing with co-moving coordinates. And so, in fact, this U mu is going to be 0, 0, 0, 1. So the for velocity will have spatial components which are 0, and the time component which is 1. Remember, the square of the for velocity is always equal to -1. And so that is all there is to it. And the fact that they will be functions of t only will also simplify the solution of the field equations by quite a bit. And so one equations we want to solve is the set of relativistic field equations, which is right here, right? Nevertheless, we also should remember that the energy momentum tensor is covariantly conserved, right? So even before we try to attempt to solve the field equations, we can write down the energy momentum conservation and solve that. Energy momentum conservation tells us that T mu nu semicolon nu is equal to 0. Well, this is a covariant derivative, right? So the covariant derivative, remember, is the ordinary derivative plus, in the case of a rank 2 tensor, there's 2 extra gamma terms that come in. And so this thing is covariantly conserved. And so we can work that out if we have this expression, right? Remember now, the rho and the p, they only depend on t. The u mu and u nu's have that form, so there's not much to it. And the g mu nu, of course, is given by the Robertson-Walker form, right? So this equation, even before we write down anything related to the field equations, just gives us that r cubed times p dot is equal to d by dt of r cubed times rho plus p. When you write it down explicitly, and in fact there's only one equation, because the other equation is something like dp by dr is equal to 0, which says that the pressure should be not change in r, right? It should be just a function of t. So we have this equation, and in fact, even before we say anything that is associated with the field equations, we can, for example, conclude that if you have non-relativistic matter, then for non-relativistic matter, the pressure is negligible, and we just have a rho of t, right? Non-relativistic matter, the pressure is negligible. So that means that for non-relativistic matter, this pressure here is 0. So we have r cubed times rho d by dt of that is equal to, in fact, 0 because the pressure is 0, right? So in this case, we have that already rho of t goes like 1 over r cubed of t, right? And if the pressure is 1/3 of the density, so this is for matter, for radiation, rho of t, again from that equation, goes like 1 over r to the 4th of t for radiation. So this is pressure equal to 1/3 times the density. So in fact, we can derive that already even before looking at the field equations, right? So get that out of the way, and right. So we will remember later on that this result, of course, matter plays a dominant role in the evolution of the universe. That covariant energy momentum conservation tells us that the density will go like 1 over r cubed, and that is something we get right away. So now the other thing is that at some point we are going to be faced with comparing what we're discussing here to observation, right? And so relate to observation, right? And the things that people observe are, for example, the Hubble constant, right? And so the Hubble constant has to do with the way universe expands. And of course, in this model, the expansion of the universe is determined by the scale factor, right? Now, the Hubble constant is essentially a velocity, right? So here, h naught is equal to r dot of t naught divided by r of t naught. So the Hubble constant is the rate at which the universe expands, and it is, of course, measured today, right? So t naught equal today, right? Today, right? And so this, of course, is not necessarily a constant, because we'll see that from the field equations, this ratio of r dot over r changes over time, right? But today, when we look at the universe, it looks like this expansion rate is pretty much very close to a constant. Usually, by the way, the Hubble constant is measured in kilometers per second per megaparsec. And so I think one usually writes it as h naught is equal to 1,000 kilometers per second per megaparsec, I believe, and times h, right? But times little h. And that little h is nowadays is about 0.73, I believe. And so this Hubble constant is kind of known. It's kind of 100 or 1,000? Good question. 100. I think it's 100, right? Yeah. So that number is reasonably well known, and so it is one quantity in which we can make contact with when we solved these equations. So now we have to deal with the rest of the field equations, right? And so the first thing we notice is that the metric, right, that the metric that you get from there is diagonal. The metric is diagonal, right? So in fact, we can read off immediately what it is. The GTT is 1, right? Right? The GTT is 1. The GRR is equal to this r squared divided by 1 minus kr squared. And the g theta theta is the scale factor times r squared times 1. And the g phi phi is the same thing multiplied by sine squared theta, right? So the other thing that we need to calculate is the components of the Ricci tensor. So for example, one now has to sit down and calculate, right? Calculate from this gamma lambda mu nu, right? The various components. Because of the symmetry of the metric, there is only a small number of these affine connection components which are non-zero. And, well, you can do this calculation by hand, or you can use Mathematica to do it, right? And nevertheless, once you calculate the components of the Ricci tensor, that is diagonal 2. That comes out diagonal 2. So it means that there is only 4 components which are non-zero: RTT, RRR, R theta theta, and R phi phi. And the RTT part is just simply 3 times R double dot divided by R. As I said, the RTI, which is an off-diagonal component, is 0. And the Rij is equal to minus times 2k plus R double dot plus 2R dot squared times G tilde ij, where the G tilde ij is the part that you get from the curly bracket. So this is the part that gives you the G tilde ij. So it's the spatial parts of the metric, but with the scale factor taken out, right? So that means that G tilde RR is equal to 1 over 1 minus k R squared, and G tilde theta theta is equal to R squared, and G tilde phi phi is sine squared theta times R squared. And the rest are 0. So G tilde ij is equal to 0 for I different from j. Right? And, well, we're basically at the stage where we can write down the field equations, because what we are going to do at this point is, in fact, write the field equations in terms of the Ricci tensor appearing on the left-hand side by itself. So we're going to write the field equations as R mu nu is equal to minus 8 pi g times T mu nu minus 1/2 G mu nu times T lambda lambda, as we have done already in a number of cases before. And so we have to figure out what this part is. And this part here, the TT part, is 1/2 rho plus 3p. And the IT part is 0, and the IJ part is 1/2 rho minus p times R squared of T times G tilde ij. Right? And so that leads us to the field equations, which I'm going to write down, and then we'll stop. So the TT equation is that 3R double dot is equal to minus 4 pi times G times rho plus 3p times R. And the RR equation is equal to R times R double dot plus 2R dot squared plus 2k, remember k is this parameter which is 0 or plus or minus 1, is equal to 4 pi g times rho minus p times R squared. And plus the equation for energy conservation, which we wrote down before. And so that's where we'll leave it, and then next time we'll continue on discussing what comes out of these field equations. You can in fact eliminate from these equations, you can eliminate the R double dot and write it just in terms of the R dot, so we're going to do that next time. So I think we'll stop here.